Combining the concept of acid-base and also the chemical equilibrium that we have discussed before, now we will see the acid and base equilibrium. So first, we know right away that we have a strong acid and weak acid. We also have strong base and weak base. If we have a strong acid, for instance, HCl, so this is a strong acid. So HCl is very strong, therefore it will dissociate completely. So we only draw one arrow like this to the right side because it completely dissociates into H plus and Cl minus. Therefore, say we have a concentration of 0.1 molar of HCl, it will completely dissociate into 0.1 molar of H plus and 0.1 molar of Cl minus, and we will no longer have HCl in the solution because this will be gone, will disappear, and instead results in H plus and Cl minus. However, this is not the case for weak acid. Let's take our favorite weak acid, so the acetic acid, CH3COOH. Don't forget the phase for this is always aqueous because we are working in solution. So for CH3COOH, there is a reaction that goes to the right side, making H plus and CH3COO minus. But there is also a reaction that going to the left side, where the H plus combines with CH3COO minus to result back in CH3COOH. And every time we have an equilibrium reaction like this, we will have the K or the constant, like this. So for weak acid like acetic acid, if we have in the beginning 0.1 molar, this is not going to be 0.1 molar for H plus and 0.1 molar for CH3COO minus. In fact, because it is a weak acid, most of the species in the solution is actually in this form, so the non-dissociated form, and only a little bit that goes dissociated into H plus and CH3COO minus. So the question is, how do we determine how much is the dissociation? So the percent of dissociation, or another name for this would be the percent of ionization. And further on, how do we determine the pH of the solution? For the strong acid, pH is very easy to calculate, which is minus log of H plus. So right away we can say that pH is minus log of H plus, which is 0.1 molar. So all you have to do is to take your calculator and find the minus log of 0.1, and then you will get the pH, which would be, I think, around 1. However, in this case, H plus is not going to be 0.1 molar, as we know the reaction doesn't completely go that way. It also goes that way. And in fact, only a little bit that will become the H plus. So how do we calculate the H plus? Here is where we use our equilibrium knowledge. But before that, let us discuss about the K. So before, I have mentioned to you that we have Kc and Kp. And actually, we can have a mathematical relation between Kc and Kp, where Kp is actually equal to Kc RT power to the delta nth. Delta n is the coefficient of gas in product minus coefficient of gas in reactant. So as you have seen in the thermodynamics chapter, just sum up all of the gas coefficients of the product and use it to subtract the sum of the coefficient of the gases in the reactant. So product minus reactant. So you can find the relation between Kp and Kc. R is, as usual, it's ideal gas constant, and T is temperature in Kelvin. All right. So you have to be careful here that the R will be 0.082 because we use the liter ATM over mole Kelvin. Okay, so use the one with the liter ATM because we are talking about pressure and concentration. So then again, Kp is the one that we use for only gas phase, while Kc we use for aqueous and also for gas. Now, we will talk about acid-base equilibrium, and at the later part we will also discuss about what we call as a solubility product equilibrium. And that's basically Kc. So we have discussed one of the Kc, that is Kw, which is water ionization. Next we will discuss about Ka, which associate to acid ionization or acid dissociation. And then we will also have Kb, which is base ionization or base dissociation. And on the later part we will talk about Ksp, which is the solubility product. So this will be for the later part. Now what you have to know here is that between Kw, Ka, and Kb we have another equation, and that is Ka multiplied by Kb will be equal to Kw. And don't forget, at room temperature, the Kw for water is 10 power to the minus 14th. Now let's go back to the example of a weak acid, which is the acetic acid, and then dissociates into the acetate ion and H+. So here we will have a Ka of acetic acid. So let's write it down here, Ka of CH3COOH. So if you see a Ka, this will always associate with an acid. Now, in the heart of any equilibrium problem, you will see an ICF table. So ICE table. So ICE table. I stands for initial, C for change, and E for equilibrium. For the sake of ease of calculation, let us assume that in the beginning we have 0.1 molar of CH3COOH. Now, because this reaction is an equilibrium reaction, we cannot use this as the limiting reactant. There is no such thing as limiting reactant in an equilibrium. Therefore, here we have to write down an assumption, which is X value. So this one is X, this will also be X, and that will also be X, as all of the coefficients are 1. Now in this case, because we do not have any of this in the beginning, of course the reaction will occur to the right side. Therefore, reactant will be consumed and product will be produced, as there is no product in the beginning. So this has to go that direction. Therefore, in the equilibrium, we will have 0.1 minus X, and this one is X, and this one is X. How do we find the X? Of course, for equilibrium, we can use the value of Ka to find the X. Say we have a Ka, this will be equal to X multiplied by X, so all the products powered to the coefficient, and then divided by the reactant, also powered to the coefficient. So here you can see that we will get Ka is equal to X squared divided by 0.1.X. Now, we will make another assumption, but you have to be careful with this assumption. When the Ka is small, when the Ka value is small than, in general, 5% of the initial concentration, so say that this is the initial concentration, I will write it down as HA. So an acid, initial concentration of the acid. As long as the Ka is smaller than 5% of the initial concentration of the acid, so HA initial, you can assume that X is very small. Then X is very small. Therefore, it is negligible to the actual concentration of the acid. And then we can form a new equation. Ka will be equal to X squared divided by 0.1. We do not X anymore. We do not need X anymore because X is very small that it will become negligible. Negligible. Only if the Ka is way smaller than the initial concentration of the acid, and in this case, let us use this 5% comparison. So in this case, Ka for the acetic acid, let us just say that the value is somewhere around 10 power to the minus 5th. And the HA, or the initial concentration, is 0.1, so 10 power to the minus 1st. divided by 100, you will get around 10 power to the minus third, yeah? And still the Ka, which is 10 power to the minus fifth, is smaller than 10 power to the minus third. So indeed, in this case, x is very small, so it is negligible. We can just make x disappear over here, and then we will get x squared divided by 0.1. And therefore, let's move up. If we move up here from here, we will get that the x will be equal to the square root of the Ka multiplied by 0.1. If the Ka is 10 power to the minus fifth, you can just multiply it with 0.1 and then find the square root of it, and then you will get the x. Now from here you can also see that in general we will have the x being equal to the square root of the Ka multiplied by the initial concentration of the acid. Under the assumption that the Ka is super small or smaller than 5% of the initial concentration, we can use this formula. So, now that we have determined the value of the x, we can take a look at our ice table again. And x is actually the concentration of H plus in the equilibrium. And we know that pH is minus log H plus. So pH is minus log of the H plus at the equilibrium. Okay? So pH in this case will easily be minus log X. And this is how you find the pH of the weak acid. On the other hand, we can also calculate what we call as the percent of ionization or percent of dissociation. That's the same thing. And how do we calculate this? We take the X value, which is the H plus, divided by the initial concentration of the acid again. In this case, it is 0.1. And of course, multiplied by 100%, and then we will get the percent of ionization. Remember, for strong acid, the percent of ionization will be 100% because the X or the H plus concentration will exactly be the same with the initial concentration. However, for weak acid like this, you will have way less percent ionization, and sometimes it's not even up to 50%. You have to calculate it based on this calculation.